If I would ask you to give me one name that comes to mind when you think about deep learning in Israel, your answer will probably be Lior Wolf. Professor Wolf is our first keynote speaker today. He's a research scientist at Facebook AI Research and a full professor at the School of Computer Science at Tel Aviv University. Professor Wolf has extensive experience in forming, advising, and heading R&D at multiple computer vision startups, and his research focuses on computer vision and deep learning and includes topics such as face identification, document analysis, natural language processing, digital panography, and video action recognition. Professor Wolf will give a talk on the ongoing revolution of unsupervised learning.
Hi, good morning. Thank you very much for inviting me here and for the introduction. Let's make it completely informal. If you have any question during my talk, just raise your hand and I will be very happy to answer immediately. So, as mentioned, I work at Tel Aviv University and at Facebook AI Research. At Facebook AI Research, we are very much focused on personalized generative models. So this means that if we have a model for text-to-speech, we want it to be personalized. We want to generate your own voice. If we have an avatar, we want it to be personalized to match your own image. So we worked a lot about both domains, avatars, and voice. There's a big difference. In voice, we apply supervised learning. So we apply deep neural network. We have our own model to achieve text-to-speech that we can fit on a very short sample of a new speaker, and it has a high degree of naturalness, and we can even fit it in the wild on videos, or basically on audio from YouTube videos. So this is done in supervised learning. What we did in Avatar was unsupervised. So we have a large collection of face images, and we have a large collection of avatar images, and we want the computer to learn by itself to map between the two. We don't want to give matching images. I'm not going to talk about this specific work because Yaniv talked here last week about the earlier version of it, but I will just say that this started our interest in unsupervised learning, and a few months after it came up, a few other contributions by other groups also came up. And they all showed quite amazing stuff. So if you consider the discogram work, it showed that you can, in a completely unsupervised way, map between two very distant domains. Let's say between handbags and shoes. You can find the mapping between a shoe and the matching handbag in an unsupervised way, without any matchings. And then there was the cycle gun work, which showed that you can do very high resolution mapping in an unsupervised way. And even in NLP, you can translate between languages in an unsupervised way. So this is all very exciting. These kind of projects, contributions, they all use what is known as circularity. Circularity is an idea that came up by multiple researchers at once. Basically, it means that if you have two domains, you have the X domain and you have the Y domain, and you have a mapping function G from the X domain to the Y domain, and you start with the sample in the X domain, you map it with G to the Y domain, then you map it back with the inverse function F. You want to get back to the original sample. This is the idea of circularity. Very simple. Of course, you can apply it in the other way as well. You start with an example in the Y domain, move it to X and back. You want to get the same original sample. So this was a very nice result. They showed excellent applications of it. Then in last NIPS, we presented something else. We said, okay, you don't really need to map in both directions at once. It's enough to map in one direction. And then what we do, we take two samples from X, we map them to Y, and we say that we want the distance between the samples in X to be highly correlated with the same distance after doing the mapping. So why would this even make sense? Let's say that you map between horses and zebras. If the two horse images are similar, then after the mapping, the two zebra images are expected to be similar. And if we are talking about another application, let's say the application of mapping between handbags in this column and shoes in this column, then we were able to show that the mapping that you obtain is actually very close to a fixed permutation in pixel space. So this is the fixed permutation that approximates this mapping G over here. So in order to make a loss out of this, we normalize the distances in both domains. We get the two normalized distances, D1 and D2, and then we compute the sum of L1 distances for just random pairs before and after. We use L1 distance. It's more stable than just using correlation. And of course, we are using GANs as well. Like almost all work that I'm going to present is using GANs. I'm not even going to talk about GANs. By this point in time, I guess everybody here knows what are GANs and how they are used. So in our experiments, if we apply this method of correlating between distances, we get state-of-the-art results for mapping better than what you can get with circularity. So up until this point, we saw two options for learning to map between two domains in an unsupervised way. So we learn in an unsupervised way semantic mapping between the domains. So this actually brings up the question, what is semantic? What do we mean when we say that we map in a semantic way between two domains? There could be many mappings between the domains. We are in the unsupervised setting, but we get the one mapping that we want, the semantic mapping. How come? So let's look at a simple example and try to realize what's going on. So let's assume that our domains are very simple, just two line segments in 2D, X and Y. So the first domain X is the line segment on the bottom. The other domain Y is the one on top. And let me ask you a very simple question. Assuming that the points are distributed evenly in the first and in the second domain, how many mappings exist between the two domains? How many ways are there to map between points in the line segment X to points in the line segment Y? And so, infinite number of points, okay? And it's not hard to see, like, wherever I go, people would agree there is an infinite number of mappings between the two domains. So let me ask another question. How many mappings are semantic? How many of these mappings between X and Y you would call semantic? Okay, so it really depends on the crowd. Some crowds say it depends what is semantic and so on, but almost always I can get the crowd to agree that these two mappings are semantic. Either the identity or the mirror one. They stand out as being more semantic than any one of the infinite number of mappings that you can get. So let me ask, what is so special about these two mappings? Okay, so one answer, they are obvious. My answer is, those are the only two mappings that you can implement with a neural network of one hidden layer with two neurons. So if you are looking for the simplest possible solution, it's the one in which you have a neural network that has only two neurons, two hidden neurons, and then there are only these two mappings. We can prove it very easily. Those are the only two mappings. So our definition of semantic is simple. So it's a version of Occam's razor, basically. We say semantic means simple. How do we measure simple? Our definition of complexity is very simple. We just count the number of layers. And we're able to show that the number of minimal complexity semantic functions like this is very small. So most of the time you would get just one mapping if you insist on using a small network. So this is a nice theory we came with, and it actually has algorithms that come out of it that enable you to get improved results. It also has a few predictions. So one prediction is that you don't really need circularity or to preserve distances. You can get perfectly good mappings between two domains in an unsupervised way just by using GANs. So circularity, distance, so on, it helps, but 95% of the way it is GANs, and does just improve a little bit on top of it. This is a bit surprising because if you read the literature, of course the literature emphasizes the novelty, you would get the idea that you need the contribution in order to do it, but actually the GAN does most of the work. So let's look at this sample. What you see here on the left is the input image. And then you can see on the right the mappings, let's say, from male to female for many numbers of layers. So if you go, let's say, this sample over here. This is a male. Okay. So let's say that I want to map between males and females. So this is the mapping between a male, and you can see here the mapping to the matching female. And what you can see over here is that if you select the right number of layers, you get the mapping which is the semantic one. If you select too few layers, then you get an output image which doesn't make much sense. It's not in the target domain. If you select too many layers, as you see on the right side, then you lose the semantic information. You get a mapping from a male to a female, but it's not the same male in this example. So this is the second prediction. It actually says that you need to tune the number of layers very carefully in order to get the right solution. So it's not really completely unsupervised. The one who's actually doing the project is controlling the architecture, and they select the best architecture in order to show you the best result. So we wanted to be able to get rid of this human in the loop, this eyeballing capability in which you look at the result and you select the best architecture. And in order to explain what we did, let me go back a little bit to supervised learning. So this is, for example, a system done in collaboration with Orbograph that reads banknotes, basically checks. And in any application, in any computer vision application that you have, it's not enough to give a prediction. You also need to give a confidence score. Tell how sure you are in the reading that you have. And this is what we did here. What we did is to train a second network, this network, in order to predict the confidence that you have. So those are the most certain readings. Those are blurry inputs, so we are less sure about the outcome. So the question is, of course, can you do it in an unsupervised way? So in unsupervised learning, you don't have samples to train the first network. How can you train the second network that trains confidence? So luckily, using this theory that we came up with, we had a follow-up work in which we have the following method for measuring success in unsupervised learning. You train your first mapper, G, between the domain X and the domain Y. And then you train a second mapper, G2, that is also a mapper between the domains, but is as distant as possible from G1. And then we say that the error that you have to the ground truth is smaller than the error that you have between G1 and G2. So this is a very simple way to get abandon the performance, because you train the two networks. It's very easy to measure the disagreement between the two networks. And this is a bound on the error. So what can we do with this bound? Well, first of all, we can design a stopping criterion for training guns. So it's well known that deciding when to stop the gun is a pain. People just look at the images and decide. What we're able to show is that there is a very high correlation between the bound, and which is here in red, and the actual error, which is in black. So it's a very tight bound on the error. We can do more. We can select parameters in an unsupervised way. So what you see here is basically the graph of the iterations that we get for an algorithm for parameter selection. It's called hyperband. It's a supervised learning algorithm. We plug in our bound instead of the validation error, and we're able to get a much better solution when we optimize for the learning rate, the batch size, and the number of layers. But there is even more. The bound that we have is per sample. So just like in the check reading example, you saw that for every specific sample, we can predict the error. Here too, we learn a mapping in an unsupervised way, let's say between handbags and shoes, and then we are able to say, well, for this handbag, I'm sure that the shoe is matching. For this handbag, I really don't know. And this is done in a completely unsupervised way without any matching. The examples that you see here are for edges and objects where it's easy to measure the error. The error is not well defined for handbags and shoes, for example. And you can see there is an excellent correlation between the error that you get and what the bound predicts. Is there any question up to this point? Please.
You assume that there is a clear mapping?
What do you mean by clear?
You assume that there is a clear mapping between handbags and shoes? There has to be a mapping? Is it possible that there will be two domains that do not have a clear mapping between them?
So it is possible that there would be domains where the mapping that you need to come up with is a complex mapping, and then you won't be able to find it, or it's infinite complexity, and then you would never be able to learn it. We are dealing with domains where, as humans, it's clear to us that there is a mapping, and we want the computer to be able to recover this mapping. But there are domains where there is no mapping. You would have to work very hard, have a very complex mapping, and after you find some network, it wouldn't make any sense to you as a human when you look at the images. Any other question? Okay. So up until now, we talked about mapping between images. So one image domain to another, and there is also work on mapping between one language to another in an unsupervised way. But we're actually able to do better now, and we're able to map between images and text. So imagine that you have a large collection of sentences, a large collection of images, and you want to learn the mapping between them in an unsupervised way. So those are the results that we get. For example, you have the small white and brown spotted bird, and then you have these images that we retrieve on the right, and the same we can do for flowers. Those are two very popular benchmarks for this problem. And this is the first, as far as we know, work that is able to do it in an unsupervised way without any matching between the text and the images. You can also map between difficult image domains. For example, you get an image, you get the top half of it, you get the bottom half, and you want to match between the two. In a supervised way, it's very easy because they are correlated. In an unsupervised way, none of the existing algorithms is successful. We're able to achieve this using the same algorithm that is going to be published in CVPR. This is, for example, the results for cycle gun and disco gun. They fail on this problem. So far we discussed work done in collaboration. I should mention with Sagi, with Tomer, with Yedid, Adam, Noam, Elia, and Yaniv. Are there any questions up to this point? Yes, please.
Can you recognize the model of a car based on its photo?
The model of a car based on?
Based on its photo.
Okay. Can you recognize A based on B? What is A and what is B?
A is the car, a photo of the car. B can recognize its maker and model.
So this is something that is being solved in supervised learning all the time, right? So are you asking, can you do it in unsupervised way?
Yes.
So assuming, for example, that you have a large collection of cars and a large collection of models. What kind of information can you use in order to do it in an unsupervised way? So the only information that I can see that you can use is that the images of the car are correlated for the same maker because models of the same, let's say you buy a Mercedes, it's similar in its design to other cars from the same maker. And also in the models, you can see these correlations, and then you can see other types of structure. For example, the model numbers tend to get higher with the size of the car. And you might be able to do something. I'm not sure, it depends really on the data and how much structure there is in the data. When you do something in an unsupervised way, what you basically do, you fit two structures together. If the structure is rich enough, you are able to do it. So let's say that you try to do a PCA in the first domain, a PCA in the second domain, and see if there is any matching. When you first asked, I thought, well, this is probably impossible. But thinking about it a little more, I think that with the structure that you have in the image domain and the structure that you have in the model names and maker domain, you might be able to do something. Very easy in a supervised way to learn how to do classification in images, right? So supervised is easy. Other questions? Of course. Yes. So the images, the distance that we use in what the NIPS work that I presented, it's a simple L2 distance, and this actually attests to two things that we learn from it. Well, first of all, it's very surprising because in computer vision, we spend so much time learning distances. But the main getaway message is that unsupervised learning, just like supervised learning, it wants to succeed. You just need to give it a little push. The role of this distance preservation between the domains is just to make sure that out of the solutions, you select the correct solution. The solutions emerge, and you just need to give it a little push in the right direction. So you can use very, very simple distances.
Let me ask it. Can you hear me? Yeah.
Yes.
Let me be more specific about my question. If I had zebras and horses, and most of my zebras are centered, and I have all of a sudden a zebra at the upper left part of the image, then its distance from all the other images is going to be huge, okay? And if I don't have a horse in the upper left part of the horse domain, how will I, or even somewhere, how will I ever be able to learn how to transform this particular zebra?
Okay, so of course, if you don't see something in the training set, you probably won't be able to generalize too much. But the distance that you compare is not between a pair of images in the horse domain to a pair of images in the zebra domain. It's the pair of images in the original domain and the pair of mappings that you get in the other domain.
And the pair of, sorry?
Mappings, after you transform with the function G that you learn. So it doesn't mean that there need to be these images that you actually transform to. Those images are generated by your system, and you just check that the generator has the nice property that you want to have. It's a property of the generator. It's not a property of the domains. We also had a few other contributions in unsupervised learning recently. Multiple domains. Let me not get into it. I only have 1 minute. But let me just share my personal conclusions from this very intensive year of working in unsupervised learning. So, first of all, unsupervised learning, as we learned this year, is much more than clustering or density estimation, those classical problems. It's much more about analogies, making analogies between distant domains, learning them in an unsupervised way. So this is very much related, I would dare to say, to the way that we as humans think in analogies, transform information between domains in an unsupervised way. This is very much exciting because if you look at the cognitive science literature, if you look at the machine learning literature, there wasn't anything over there that could predict the success of such completely unsupervised methods. So this is a theoretical challenge that we had to tackle. We now have a theory about it. The theory is very nice in the sense that we can get algorithms and predictions out of it, and there is definitely more that can be done in this domain. Can you solve everything with unsupervised learning? Of course not. For example, the sequence-to-sequence examples in voice that I started with, but you can get a lot of work done in unsupervised learning, and you can learn a lot about about the cognitive abilities that we have and what is possible to do with very little supervision. Thank you very much.